Okay, in this video, I'm going to do Riemann sum in depth. And instead of just saying do the limit of the Riemann sum, I'm really going to calculate exactly what the limit of the Riemann sum is and do all that. And to start with, I have this really fun thing in Desmos that I found. All the other things in Desmos this year I have made myself, but this one I just Googled and found, and it's perfect. It's exactly what I want. We have a function, that's the black curve, and we want to know the Riemann sum under it. And somebody has drawn all these rectangles that fit it. The green rectangles are above the x-axis. Those are going to add to the integral. And the red areas are below the x-axis. Those are going to subtract. So the Riemann sum is going to be the sum of all these green rectangles minus the sum of all these red rectangles over here. And there's a slider, there's a really nice slider for the number of intervals. And as you increase the number of rectangles, the rectangles get thinner and thinner and thinner. And as you do that, as you increase that, the sum, the value of the Riemann sum, is getting closer and closer to a particular number. So let's see what happens as I increase these things. So the value of the Riemann sum is getting closer and closer to a number, and that number is the integral. So in this case, the integral works out to 3.2196. That's not very satisfying. Let's do a better example. Let's do from a equals 0 to b equals pi. Is going to let me do pi, and I want to integrate the function sine of x. The integral from 0 to pi of sine of x. And so you can see, if you use fat rectangles, you have all these parts you're kind of not doing a great job estimating. But as you increase the number of rectangles, you will get closer and closer to the true value. So here it's 1.98. And as you increase the number of rectangles, it gets closer and closer to the true value. It turns out the true value is 2. The value of this integral is 2, and we're going to see that soon in the course, why the integral is 2. So this Desmos thing is showing you how this works. And I want to do this in detail for a very simple function. I'm going to do the function f of x is 3x. And so we can see how this works one more time. We can make some number of rectangles. And you can see that with 11 rectangles, you're not doing a great job estimating. There's all this area you're leaving under the curve. It's a bad estimate. But as you increase the number of rectangles, you get closer and closer to the true value. And the true value in this case, 1.47. The true value is going up, 1.48, 1.485. Let's see, can I do even more? Let's make 1,000 rectangles. 1,000 rectangles. I need to... Can I zoom out a bit? Okay, yeah. 1,000 rectangles. As you increase the number of rectangles, the area of the rectangles is getting closer and closer to the true value under the curve, and that true value is actually 1.5. Here we got up to 1.4985. And so in this video, what I'm going to do is I'm going to find an exact formula for this S. S is the sum of the rectangles, the Riemann sum. I'm going to find an exact formula for S in terms of n, the number of rectangles. And once I have the exact formula, we can use our limit laws to find the limit and prove that the limit is actually equal to 1.5. So that's what we're doing in this video. A bonus video. Maybe let's not call it bonus. Bonus has the wrong connotation. It's extra to what we did before. And this video is a proof that the integral from 0 to 1 of 3x dx equals 3/2, or also known as 1.5. And how I'm going to prove that? So the integral from 3x dx is the limit of the Riemann sum. So this is the limit as n goes to infinity of a certain sum from k equals 1 to n. You've got this xk star. You've got xk minus 1. So we're going to evaluate this thing and prove that the limit is 1.5. So there's going to be 2 steps. Step 1 of the proof is find a formula for Sn, which is going to be the sum from k equals 1 to n of f of xk star, xk minus 1. And then step 2, do the limit as n goes to infinity of Sn, and show that the limit show limit as n goes to infinity of Sn equals 1.5, also known as 3/2. Okay, so that's what we're going to do. By the way, you can also see it's 3/2 just by using base times height divided by 2, right? So we're doing the integral of a triangle. It's the function 3x. We're doing it from x equals 0 to x equals 1. So it's a triangle of width 1 and height 3. So we know the area is 3/2 from the formula for a triangle. But we're doing it with a Riemann sum. So, and the definition of an integral says use a Riemann sum. Okay, and I lied when I said I'm going to find the formula. I'm only going to find the formula in the special case. The special case I'm going to do is the right uniform Riemann sum. So I'm not going to do the general thing because the general thing is quite complicated, but I'm going to do the right uniform Riemann sum. So what is the right uniform Riemann sum? Sn is the right uniform Riemann sum. This is the right uniform Riemann sum. And it's for the function f of x is 3x on the interval 0, 1. So I'm on the interval 0, 1. A Riemann sum is always the sum of n things. The n things are supposed to be the height of the rectangle, f of xk star, times the width of the rectangle. In our special case, because it's a uniform Riemann sum, the width of the rectangle is always a constant. It's always delta x. The height of the rectangle is also the special point xk star where you evaluate. Because it's a right Riemann sum, it's always the right endpoint xk. And you can check that in the formula we had earlier. In this particular case, there are n divisions. We're doing the sum with n divisions. And so delta x is b minus a divided by n. F of xk, the formula for xk is a plus delta x times k. So you start at the left endpoint a, and you move over k times, and each time you move by delta x. So the position xk is a plus delta x times k. Oh, and delta x we said is b minus a over n. In our particular case, b is 1, b equals 1, that's the right endpoint, and a is 0. So this simplifies yet again. This is the sum from k equals 1 to n of f of 0 plus 1 minus 0 divided by n times k. b minus a over n is 1 minus 0 divided by n. And that's quite simple. This is the sum from k equals 1 to n of f of k over n times 1 over n. That is the Riemann sum Sn for a function on the interval 0, 1 using the right uniform Riemann rule. Okay. And our particular function is the function 3x. So I actually care about this function, the sum from k equals 1 to n of 3k over n times 1 over n. That's what I want to do. Now what's going on in this sum? So the sum says loop over all possible k values. K equals 1, k equals 2, k equals 3, and add them all up. But there are these terms, there's a 3, and there's these n's, and those aren't changing from term to term. So if you were going to write this out, this would really be 3 times 1 over n squared plus 3 times 2 over n squared plus 3 times 3 over n squared plus dot, 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 all the way up to 3 times n over n squared. That's what the sum means. And because the factors 3 and n squared are the same in every single term, you can just factor those out to the front. So this is the same thing as saying 3 over n squared times the sum from k equals 1 to n of k. And you could write this, you could perfectly well write this as a sum 3 over n squared. It's the sum 1 plus 2 plus 3 plus dot, 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 all the way up to plus n. It's the sum of the first n numbers. That is what Sn is equal to. So that's what we got to do. We got to add up the first n numbers. And we would like to find a nice formula for this that we can take the limit of. Now, how are we going to do that? This is an amazing trick that I love. I think this was the first trick I saw. I think I was like in grade 2 or something. And I like, this is the moment that I fell in love with math, was this trick right here. What you do is you take the sum and you write it backwards. You write it backwards. So Sn is 1 plus 2 plus 3 plus all the way up to n. And equally well, you could write it the other way. You could write it as n plus n minus 1 plus n minus 2 all the way up to plus 1. So you could add up Sn either way. You could add it up 1 plus 2 plus 3 all the way up to n, or you could start at n and work down. So you can do either way. It's both of them are equal to Sn. And here is the miracle. If you do this equation plus this equation, add up what's going on the top line to what's going on the second line. On the left-hand side of the equation, you have 2Sn. On the right-hand side of the equation, what do you have? Okay, you have a constant factor of 3n squared. But what else do you have? You have 1 plus n. 1 plus n. That's n plus 1. Then you have 2 plus n minus 1. 2 plus n minus 1. That's exactly n plus 1. So the first term, n plus 1. Second term, n plus 1. The third term is 3 plus n minus 2. That's still n plus 1. So even though the terms are all changing, they're exactly set up so when you add them together, no matter which term you're on, you always get n plus 1. The last term is still n plus 1 as well. Okay, and now we can add it up. Before it was some complicated thing, all the terms were changing. But now it's n plus 1 added up n times. N plus 1 added up n times. And what happens if you add up n plus 1 n times? You get the multiplication. So 3 over n squared times n plus 1. So we did the sum. We figured out what Sn was by doing this trick of writing it backwards and adding it to itself. Beautiful trick. Okay, now we can cancel out a little bit. 3 over n squared times n. That's the same thing as saying 2Sn equals 3 times n plus 1 divided by n, or Sn is 3/2 times n plus 1 divided by n. So now we have an explicit formula for Sn. We can check, let's make sure that we did it right. We can check in Desmos that we have the right thing. So let's go to Desmos, and we have this Riemann sum formula. And so I'm just going to make sure that everything's set up right. Left endpoint 0, right endpoint 0. Number of intervals is n. Choice of method, c equals 0 for left-hand sum, c equals 1 for right-hand sum. We want c equals 1. We did the right-hand sum. So let's do the right-hand sum. And we have this formula for s, and the computer is calculating what it is. But we can also try our formula and see if it gives the same thing. So let's try our formula. We said our formula is 3 over 2 times n plus 1 divided by n. And if it works, when I type in n, we should get 1.503. Look at that, guys. We did it. So we found the formula for the area of the green rectangles in terms of n. So it's this crazy complicated sum, but we figured out an exact formula for it. And now that's it for this step. That was step 1, find the formula. Step 2, find the limit. Step 2, find the limit. So the integral from 0 to 1 of 3x dx is equal to, what is it equal to? It's the limit as n goes to infinity of Sn. That's the definition of the integral. That's what it means. And in this case, what is that? That's the limit as n goes to infinity. 3/2 times n plus 1 over n. This is a limit we know how to do. We did this limit when we did limits. Why did we do limits at infinity? We haven't used them all year. The reason we did limits at infinity is to do this limit right here. 3/2 is a constant factor. This is an infinity over infinity type limit. When you have limits like this, you could divide the top and the bottom to make them more tame. So n plus 1 over n, divide the top and the bottom by n. 1 plus 1 over n divided by 1. So this is a infinity over infinity type. And we're going to solve by dividing the top and the bottom by n. Okay, and if you do that, you get 1 plus 1 over n divided by 1. This one, the ordinary limit laws apply. So you get 1 plus the limit as n goes to infinity of 1 over n divided by 1. And this limit we know is 0. So 3/2 times 1 plus 0 divided by 1. The final answer is 3/2. So everything we did, all that work, shows that the integral from 0 to 1 of 3x dx is 3/2. This is how you do limits sort of by hand. This is the equivalent of doing the limit definition of a derivative. This is the limit definition of an integral, and it really is a lot of work. You got to figure out these sums. Fortunately, you never have to do this because there is an easier way. And that easier way is the fundamental theorem, which we're going to learn next class.